Hello class, this is Miss Jacoy. So I want you to try these. I know they're labeled 5 and 2. That's because I smashed up 2 different papers together. So do 5 and number 2, try them first on your own, and then come back to take notes to go over it. Alright, now that you've attempted 5 and 2, if you haven't, pause it. So first, read it. It's a 40-gram chunk of aluminum is dropped into a cup of water that is initially at a temperature of 30 degrees Celsius. After they've reached thermal equilibrium, the final temperature of the entire system is 28.5 degrees Celsius. So not even doing any calculations, what does the final temperature of the water tell you about the initial temperature of the aluminum? So think this was our initial for the water, and this was our final for the water. So what does that tell you about the initial temperature of the aluminum? Hopefully you can tell, well, it went down. The water temperature went down, which means the only thing that could have caused it to go down is the aluminum. The initial temperature of the aluminum must have been much lower. And so the aluminum had a low temperature. And what direction does the heat flow in this situation? In this situation, the heat flowed, so the water heat, I did not like the way I wrote that, the heat from the water flowed to the aluminum. So if you were to say draw a picture, if this is our aluminum, it probably should be gray. And this is our water. Heat would go from the water into the aluminum. So the water is losing heat, the aluminum is gaining heat. Alright, then for the calculations, if the cup is full of 45 grams of water, what is the initial temperature of the chunk of aluminum? And this is our heat capacity. So we want to set up a dual equation. We have to both know how much heat the water lost, because that's going to be equal to the amount of heat the aluminum gained. So we want to do heat for our water first. So in case you're not sure, the cup is a Q equals MC delta T. The Q, we don't know yet the Q for our water, but we do know our mass is 40 grams. We know that C for water is 4.18. If you haven't memorized it yet, that's just a number a lot of things take for granted that you have memorized. And then you know your change in temperature was your initial, is your final minus your initial, so it'd be 28.5 minus 30. So then do the math. If you subtract it, that would be 1.5 times 4.18 times 40, which is, and negative 1.8. It's 250.8 joules, negative 250.8. So we know that the Q is 250.8 positive for, and I'm just going to start writing down here because I'm running out of room. So for the aluminum, the Q is 250.8 joules positive because it gained energy. We know that the mass was 45. Oops, read that wrong. The cup is 45, so I gotta redo this. This is 40, which always goes to show, read the question carefully. This is 40 grams, that's the chunk of aluminum. And this is 45 because the water is 45. Let me quickly change that. So instead be negative 282.15. So this would be a positive 282.15. It's equal to 40 grams, our mass, times our C is 0.911. They gave it to us. Joules per gram Celsius. And then we know the final temperature, because the final temperature of the entire system is 28.5, and then you're subtracting your initial. So first, I often like to treat this as just one whole thing. We don't know the total change, so we're going to divide these out on both sides. And that will give you 7.74 is equal to your delta T, which we now know at this point 7.74 is equal to, it's our final minus our initial. So there's a couple ways you could do this. You could just look at it and think, what do you have to subtract? Or you can move this over, make these both negative, and then know that it's the positive version of, let me do the math on that. So it'd be negative 20.76. But since they're both negative, it started at 20.76 as its initial temperature, much colder than water, and it cooled the water down by about 1.5 degrees. So your T initial, to restate, is 20.76 degrees Celsius. Alright, I'm going to clear it. Alright, looking at problem 2. An ice cube that's taken out of a freezer where it has been frozen at negative 6 degrees Celsius and is dropped into a cup of water that has an initial temperature of 27.4 degrees Celsius. So A is just compare the motion of the molecules between the water and the ice cube. So if you think of your little ice molecules, they are actually held together with quite solid hydrogen bonds. So even if they're moving, they're stuck together, they're just moving in place. So we can say they're almost just wiggling. Alright. Additionally, this water is very cold, so it's moving even less. Water, on the other hand, there's no set pattern. They can move wherever they want to, as long as they stay roughly together. They can't leave their container. But beyond that, they get to go wherever they want. They're also warmer. They're moving much quicker. So these would wiggle. So the ice essentially would wiggle in place, and this would be very slow. This would be much faster. Not as fast as a gas or hotter water, but much faster than our ice. So then again, compare the total amount of thermal energy. Well, since one is colder, the water has a lot more thermal energy than the ice because it's a higher temperature. It's also a different phase. Liquids generally have more thermal energy than their own state in a solid state. So if they're the same substance, such as water and ice, or both H2O, they have more energy in the liquid state than they do the solid state. Alright, and then C, when the ice is placed in the water, in which direction will the heat flow? So, in case you haven't figured this out yet, that's the lemonade problem. And hopefully the more we've been talking about it, every time we say it, we talk about the heat flowing from the hotter place to the cooler place. The water is hotter. So heat will flow from the water into the ice cube. So heat always goes from a place of higher heat to lower heat. So the heat always moves in a direction so that it essentially heats up whatever is cooler. And it's always heat that moves. There is no such thing as cold moving. It is the lack of heat or the heat going the opposite direction that you feel. Alright, D, if the specific heat of the ice cube is 2.1 joules per gram degree Celsius, and the ice cube has a mass of 30 grams, how much heat will be required to bring the ice from negative 6 to 0 degrees Celsius? So this is similar to what we did today in class. So since this is a temperature change, it is Q equals MC delta T. We know our C is this. This is our mass. This is our change in temperature. Remember, it is final minus initial. So it's just Q is equal to 30 grams times 2.11 joules per gram degrees Celsius. And this is final minus initial, so 0 minus a negative 6 will give us a positive 6. Alright, and then multiply. And that gives you 379.8 joules of energy. Alright, so that's the first one. And then E is how much heat is required to melt the ice cube. So remember, there's no temperature change. If there's no temperature change, the equation we're looking at is mL. To do this, you would have to know that the latent heat of ice is 334 joules per gram. That's a standard number. If you have internet, you can always just look that number up. So it'd be Q is equal to the mass, 30 grams, times latent heat, 34 joules per gram, multiply, will give you 10,020 joules. So to essentially melt all of our ice, we'll need 10,000, basically I'm adding them. So the total heat, this is not a question, just something to think about. The total heat we need would be these added up. Should be essentially 10,400 if we were to round it. So this is roughly 10,400 joules of energy we would need. Alright, hopefully this has been informative. Remember, Wednesday, we have a quiz. It is basically, it can be drawn from pages 15 to 21 and pages 5 to 8. And then due on Friday is your 7 sources plus your outline.